Alright guys, so today we're going to go ahead and go into the beginning of the next chapter. Ooh. So, we're going to take a look at antiderivatives and integrals. So, I ask you, what does an antiderivative sound like? Well, to me it sounds like the opposite of a derivative. Okay, keeping that in mind. Suppose you're asked to find a function whose derivative was 3x squared. So that being said, we know that if I were to take the derivative of some kind of random function, we're just going to call it f, be 3x squared. There you go. Okay, well, what would that look like? What would this function look like? Maybe x cubed? That leads us into the definition of an antiderivative. I'm going to make this a little smaller. So my definition is a function f is an antiderivative. No, I missed a t someplace. Antiderivative of lowercase n, f, on an interval, capital I, if f, big capital F prime of x equals f of x for all x in I. Which leads us to a theorem. If capital F is an antiderivative, oof, not right today, I'm sorry. So the the definition of an antiderivative is when the derivative of that function equals the original function, so going back and forth. This leads us to a theorem that if f is an antiderivative of lowercase f on some interval I, and g is the antiderivative of f on the interval I if and only if g is of the form g of x is equal to f of x plus c for all x where c is constant. Because, if I go back for a second, we know that when I take the derivative of constants, I get a 0. So we could, by chance, have a plus 2. Or we could have x cubed minus 1,000. Or we could have x cubed minus 7. We don't know for sure, and because we don't know, there's always that possibility, so we have to include it. Alright, so let's take a look at our examples. So when I take the integration of essentially just of 0, excuse me, I I missed something. Alright, computer, stop being difficult right now. If I take the integration of 0 of dx, that gives me a constant. I'm going to try something right now. This wasn't working the other day, but for some reason my computer's being difficult, so I'm going to try this. Maybe not. Nope. I have a pen I was trying to write with. It doesn't work. If I take the integration of a constant, because we can't use c again because we've already used it in this one, and I don't want to confuse you by saying that they would replace each other. So in this case, if I take the integration of a constant, it gives me that constant times my variable plus c, because again, we could have an additional constant going on. If I were to take the integration of k times f of x dx, I know I can pull out my k, again, k being a constant, and take the integration of a function. I can take the integration of two functions being added or subtracted together. And that's equal to splitting them up. So the integration of f of x dx. Oh, good lord. That's driving me insane. Plus or minus the integration of g of x dx. And last but not least, the really big main idea is the integration of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c, where n is not equal to -1. Something I want to point out is that you notice I have this symbol with stuff here and then a dx. It's like saying that I have parentheses around a multiplication problem. I can't have one without the other. It also tells me with what respect I'm taking my derivative to. So for example, since I have the x part, the x is saying I'm going to have my variable be an x. If it was a t, then my variable would be a t. If it was w, then my variable would be w. So that when I do take the integration of a constant, I know what variable to stick on with it. Okay, so what we can do is, I don't know why this is being so dumb. I have that 7 times my x. So what I can do is I can take out my 7. Now I have the integration of x dx. Well, x is simply x to the first. So I have 7 times x to the, well, this is x to the n, so that's 1 plus 1 divided by 1 plus 1. I think I know why it's doing that. Plus my constant of c. So then I have 7 times x squared over 2. Something is sticking in my computer. plus c. I can go ahead and multiply my 7 into the top. My answer is 7x squared plus 2. Excuse me, 7x squared over 2 plus c. Alright, next example. Again, I'm going to go ahead and take out that 3. You can take the integration of x to the first dx. So I have 3 times x to the 1 plus 1 over 1 plus 1 plus c. So I have 3 times x squared over 2 plus c. So I have 3, oops, a little too far. So I have 3x squared over 2 plus c. Alright, more examples. So I can bring out that 5 of the integration of x squared dx. So even though this is a different number out front, I can still go ahead and add 1. So I have x squared plus 1 over 2 plus 1 plus c. So I have 5x cubed over 3 plus c. Well, sometimes we can't always take the integration right away. So I don't know what a square root is, but I know that the square root of x is the same thing as x to the 1/2. So if I don't know how to take the integration of what I see, I have to change or manipulate it to make it something I know how to take the integration of. So instead of having that 1/2 or x squared there, I'm going to put it to the 1/2. So we're going to do the same idea we've done before. We have x to the 1/2. We're going to add 1. Now, would you agree with me that 1 is the same thing as 2 over 2 in this case, since I have a denominator of 2? And we're still going to divide by that same addition problem. Okay. Didn't go up front enough. Well, that gives me x to the 3 over 2 divided by 3 over 2 plus c. I forgot my plus c over here. Now, when I have a fraction over a fraction, that just grinds my gears a little. It's not mathematically correct. So we essentially have two fractions going on here. We have x to the 3/2 over 1 divided by 3 over 2. And we know we can take fractions, we know that when we divide fractions, we don't like to do that, so we're going to flip and multiply. So it's x to the 3/2 over 1 times 2 over 3. Well, top times top tells me I get 2x to the 3/2. Bottom times bottom tells me I get over 3. And I get my plus c. Alright, another tricky one. So again, we don't know how to take the integral of a cube root, but I do know that I can rewrite a cube root as a 1/3. So the integration of x to the 1/3 dx. So I get x to the 1/3 plus 3 over 3 over 1/3 plus 3 over 3 plus c. So it gives me x to the 4/3 over 4/3 plus c. Now, I don't want to have to show that flipping every time. So if you noticed in my last example, I ended up having the reciprocal be the coefficients of my fraction. So in my exponent, I have the 2/3, or excuse me, 3/2. The constant is the reciprocal of 2/3. So keeping that in mind, what is going to be my constant here? Good, the 3 over the 4. Oh, I wrote into that. My bad. Okay, well, we've taken the integration so far of little pieces of stuff. So let's go ahead and take the integration of a function. Well, I can take this in pieces, just like I was taking my other little pieces into pieces. So I can take out that 3 and take the integration of just my x squared dx. Plus, I can take out that 5, take the integration of just x to the first dx. So I can split up my integration just like I could split up my derivatives. Sorry, I lost the word for derivative there. So I know I'm going to have 3 times x to the 2 plus 1 over 2 plus 1 plus 5 times x to the 1 plus 1 over 1 plus 1 plus c. I'm going to move this down together so I have some more room because I'm running out of space. Undo, undo, undo. Control Z. Sorry, I was running out of room. So I get 3 times x cubed over 3 plus 5 times x squared over 2 plus c. Well, multiply by 3 and times by 3 end up canceling each other out here. So I just get x cubed. I don't have any fun cancellation over here, unfortunately. I'm left with x cubed plus 5x squared over 2 plus c. Alright, let's try another one. I can pull out my 7, take the integration of x to the 5th dx plus 3 times the integration of x cubed dx plus 2 times the integration of x dx. Okay, so that's 7 times x to the, anyone have an idea of what's going to come next? Good, 5 plus 1. Over 5 plus 1 plus 3 times x to the 3 plus 1 over 3 plus 1 plus 2 times x, no, it's not, x to the 1 plus 1 divided by 1 plus 1 plus c. Alrighty, this gives me 7x to the 6 over 6 plus 3x to the 4th over 4 plus, well, I'm going to end up with a 2 down here, and these guys are going to cancel. So I'm going to be left with x squared, and then plus my c. Alright, I want you guys to try these next 4. And I want you to tell me what you get. So I want you to pause the video, try them, and then check your answers. So there's the first 2. Here are the second 2. Even if you got all 4 of those, I want you to stick around because we're going to do something that I want to talk about. So that way you can't say we've never seen it. So when I have stuff to the denominator, I have to make it look like something we know how to do. So I have to simplify it. Typically, if I have x's on top and x on bottom, to simplify, what mathematical operation would I do? Get out, subtract. Okay, well, I don't necessarily have x's on top and x on bottom here. I just have x's on bottom. So I need to rewrite these so I see x to some kind of exponent. So how do we do that? Well, it's going to be the integration, maybe, of x to the negative 3rd dx. So again, I still take my negative 3, and I add 1, and I divide by my negative 3 plus 1. And I still have my plus c. Nothing's changed there. I get x to the negative 2nd over negative 2 plus c. But do I like negative exponents? No, so he goes and hangs out with my negative 2 on the bottom. And when he goes downstairs, he becomes positive again. I've got 2 more examples, and then we're good to go. Okay, so same idea. I can't take the integration because I don't have a single x to a single power. I have 1 over x to a power. So I need to make that x come up. So I have x to the negative 5th. So I get x to the negative 5th plus 1 over negative 5 plus 1 plus c. X to, negative 5 plus 1 gives me a negative 4. Just like my example before, my x has a negative exponent, so he goes and hangs out in the bottom. And that's my answer. Alright, this is the last problem. I want you to try it. Pause the video. Come check your answer when you're done. Alright, hope you got the same answer. See you tomorrow.